In this work, we present an adaptive nonlinear model predictive control architecture for aggressive quadrotor flight under uncertainty. Recently, nonlinear model predictive control methods have been successfully deployed onboard quadrotors to achieve highly aggressive maneuvers with precise tracking accuracy. The performance of MPC depends highly on the accuracy of the underlying dynamic model. In reality, however, obtaining accurate model parameters like drag and thrust coefficients can be cumbersome and prohibitively expensive. Recent advancements in system identification enable learning of sophisticated dynamic models using Gaussian processes. The learned model can be integrated within an MPC, however this comes with significant computational overhead and does not enable the controller to adapt to a changing system. To address this problem, we propose the following cascaded control architecture, which couples a nonlinear model predictive controller with a nonlinear observer-based L1 adaptive control law. To show that the adaptive control law can compensate for unmodeled aerodynamics, we fly increasing speed circle trajectories up to 10 meters per second. Our method, shown in red, outperforms a data-driven MPC based on Gaussian processes by over 70%. Even without an aerodynamic model included in the reference dynamics, we see significant performance improvements. Next, we introduce a large payload disturbance of 450 grams without updating the MPC model. This results in a mass mismatch of over 60%. Our method, shown in red, accurately tracks the desired circle trajectory despite the large disturbance. The non-adaptive MPC, shown in blue, cannot compensate for the model mismatch, resulting in significant tracking errors. We can even deliver ice-cold beer. In scenario 3, we introduce a static external aerodynamic disturbance and attempt to track the same trajectory from the previous test scenario. The non-adaptive MPC, shown in blue, suffers significant tracking performance degradation, while our proposed method, shown in red, keeps the system close to the reference despite the disturbance. Next, we fly a racing trajectory with peak velocities of 11.9 meters per second and linear accelerations of over 2 Gs, with an unknown slung payload attached. The figure shows the positional tracking error over the course of the trajectory. First, in blue, we have a non-adaptive MPC without the payload attached, and in red, we have our proposed method with the payload attached. The addition of the adaptive inner loop controller significantly improves tracking performance even with the time-varying disturbance. In one instance of this test, the slung payload hit the rotors of the quad, dislodging it from the platform. The adaptive controller was able to immediately react to the system change and save the quad rotor from crashing. For the final scenario, we fly a highly aggressive racing trajectory with linear velocities of 19.4 meters per second and linear accelerations of over 4 Gs. The controller keeps the tracking error to a minimum, allowing the quadrotor to navigate a difficult split S maneuver at high speeds. The addition of the adaptive controller is relatively straightforward to implement and offers large performance benefits relative to the non-adaptive MPC. Interested readers are pointed to our paper linked below for further details.